Uh, so welcome everyone in the event of the webinar series of the European Meteorological Society. I am Monika Lakatos, the president of the Hungarian Meteorological Society, one of the organizers of the webinar series. So first we go through the formalities. Please note that the webinar will be recorded for later publication on the EMS channels. You can ask questions by typing into the chat after the talk is finished. The chat can only be seen by the speaker and the organizers. But if you want to speak anyway, please raise your hands. On today's program, Rasmus Benestad will show in 25 minutes that how we can turn global climate model data into solutions for climate adaptation. But I would like to introduce shortly our speaker first. Rasmus Benestad is an experienced Norwegian climate scientist and modeler with expertise in empirical statistical downscaling, climate extreme analysis, and seasonal predictability. Significant contributor to international climate assessments, for example, the IPCC fourth assessment report, and dedicated science communicator, notably as a co-founder of the influential Real Climate blog. The focus of this Real Climate blog is climate science from climate scientists. So now I give the floor to Rasmus Benestad. Please share your screen, Rasmus.
Thank you, Monika. Can you see my screen?
Yes, I can see, and I also can hear you very well. So please, the floor is yours.
Thank you very much, and good afternoon to everybody, and thank you for listening. I really appreciate having the opportunity to speak to you. And I will talk about distilling reliable, robust, and relevant information from global climate models for climate change adaptation. In other words, downscaling. And I also would like to say that Julia Lutz, Oskar Landgren, Kaiser Parding, and Andreas Dobler have contributed to this material that I'm going to present. And I will present this through a couple of case studies. I will start off with Svalbard, and you can see a map behind me here is actually of Svalbard, and you can see the landscape. And if you zoom further in, you see this picture here. This is from Jansson, Haugen, Adventdalen, and it was taken August 2025, but it was in summer 2024, which was really extreme on Svalbard, with extreme record high temperatures, higher than I ever seen before. And these high temperatures do actually leave a mark on the landscape. And here you see the effect of a thawing and collapse of ice wedge polygons in a continuous permafrost on Svalbard. So what can we say about such local conditions in the future? So we know that the global climate models are not designed to provide the local details about climate. So, but they are constructed to reproduce large-scale features, large scales, and they have a minimum skillful scale. So we need to downscale the results from global climate models to local scales in order to be able to say something about the future consequences and impacts. And there are some subtle but profound aspects to downscaling. The traditional downscaling has tried to estimate each data point. And you can see here we have two examples of data. In this case, temperature, but it could also be precipitation. So the downscaling methods have tried to estimate each of these data points here for each day, for instance. Here, like throughout the year, it could be a longer time period as well. And this is a method which has been inherited from weather forecasting, and I would label this downscaling weather. And this kind of approach is also quite similar to the regional climate models used in dynamical downscaling, but also very typical for artificial intelligence and machine learning, and of course, traditional statistical downscaling. But for climate change studies, there are some problems, especially with non-stationarity and also non-representative training data. So the methods have been trained on data which represent the past and not the future, which leads to some kind of extrapolation. So another approach is to try to say something about how the statistical properties change, because climate change, we would really want to know how the statistics change more than what the exact weather would be in the future. And we know that the statistical properties are more predictable than individual outcomes. So then we want to estimate, say, parameters defining the shape of the curves of, say, probability density functions or probabilities, or the intensity, duration, frequency curves, IDFs. So here we have the typical curve for temperature. We can sort of approximate it with a Gaussian distribution or normal distribution with mean and standard deviation. And here we have for rainfall, this is daily rainfall just for the wet days. So let's start with looking at the statistical properties for Svalbard temperature. And in this case, we look at the summer temperature, summer daily temperature, and you see the gray histogram here is for daily anomalies observed on Svalbard. And then we have fitted a normal distribution, the red curve here, which is based on the mean and the standard deviation. And it gives a fairly reasonable description of the daily temperature, summer temperature on Svalbard. So the question is whether we can see how this statistics changes over time, and also how it will change in the future. So here's an example of how it has changed over time. So the previous histogram was based on the period 1991 to 2020, and the blue curve here is from 1961 to 1990. And you can see that the mean temperature has increased by 1.2 degrees between these two periods. And then we can also see, that the top of the more recent curve is actually a little bit higher, and also a bit the curve is a little bit narrower, which shows that the standard deviation has changed by a small amount, by about 4%. So, but to get a really robust results for Svalbard, we should try to downscale several sites in one go, because then we get a stronger signal to noise ratio. So this map shows a downscaled scenarios for the Barents region, and you can see there, like the different sites are marked here with the circles. And we downscaled all of these using principal component analysis to represent them to get the most signal and less noise here. And the Svalbard station is here. So now we'll zoom in on Svalbard to see what is happening there with this downscale result. This is, by the way, ensemble mean temperature from a large multi-model ensemble. So here we have the June-August average temperature measured on Svalbard. As you can see that it has been increasing recently. 2024 was by far the highest, the warmest summer ever recorded here. So we can pick one global time model and downscale it, and then we get this result here. And you see that it does, like when you compare the historical evolution, we see that it actually reproduces the observed warming fairly well, apart from the recent hike up here. And it also suggests that like the future will not bring very much more warming, but a little bit more warming. But we have a lot of models, many models. So if you pick another model, we get this result. And here you can see that this model seems to indicate that we get some of these spikes that we saw in 2024 and also in the future. But it indicates a much stronger warming in the future than in Norway's model. Or we can pick like a third model, IPCL, and we get more spikes there and even higher, stronger warming in the future, or a fourth model. And you see, like, depending on which one we pick, we get different answers, and that is not robust. So robustness means that it shouldn't matter which, like if we add or include as a model or not. Or if you look at all of the models that we have here, we have 351 available climate model simulations. Some models are run many times and some are just once. And you can see we get this mess there, and it's like, it's hard to make use of this information. But if we present this information in terms of percentiles, we see that we have the ensemble mean here, and then we have like the lowest and the highest values, and then we have various percentiles in between. To get robust results, we also need to look at other emission scenarios. This is like SSP 245, and also we should avoid looking at the maximum and minimum, but like confine ourselves to the 5th and 95th percentile. And then if you plot the results according to those criteria, we look at ensembles, and we have large ensembles here, and we can evaluate these ensembles against the historical changes. And we see that the ensembles do reproduce fairly well what we have seen before. And we can also see what effect different scenarios have here on the outcome in the future. And we see that we can actually cut the emissions of greenhouse gases, and that would make a big difference in the future for Svalbard. So this is just one method of deriving or local information or downscaling, and there are different types of downscaling which are based on different assumptions. For instance, dynamical empirical statistical downscaling. So we want to compare the two to see how they compare. They also have different strengths and weaknesses. But if they agree, then we can have greater confidence in them. So these are the RCP 5.85 MPI and ORSM, and also we have ERA 5 here, which you see here. And we see that the MPI actually gives fairly similar results as the statistical downscale ones, maybe a bit less than the SSP 585, and in ORSM is a bit below, but they're sort of fairly similar. And we can also look at the distribution of the ensemble, and we see that some models have many runs and others have only one, but they seem to have different climate sensitivities. This is not actually typical for most places. So this is more typical for the Arctic. We have some which have higher sensitivity than the others. And the question is, should we use the whole ensemble with all 351 runs, or just one run per model? So this is a little bit ad hoc, but having like a large ensemble gives us a better picture of the natural decadal variability. So it's sort of it's an ensemble of opportunity, but still it gives a fairly good reproduction of the past that we've seen. The nice thing of having some models which are run many times, like we call them SMALs, a singular model with initial conditioned runs, we can say something more about the future. And here we have two cases, Access and Canadian ESM5. And see, they do tend to behave quite a bit differently, but they also do seem to suggest that the range between like a cool and a warm summer increases in the future, which is also quite important information. And we can't really derive that from different models because they may have different climate sensitivities, but these runs have the same model, same sensitivities, but still they indicate there's like a diverging range of warm and cold years. And finally, when this runs out, we can compare the downscale scenarios with summer 2024, and we can see that for the SSP 585, this summer would be normal in 2050, but the others will take a bit longer time, and 2078 for the SSP 126. And we can also see how many of the ensemble members exceed the level of 2024. So we see that by 2100, almost all of the SSP 585 are above this level. So this was temperature. What about precipitation? And I will present another case taken from the SPRINGS project. It's an EA project called SPRINGS, which is about climate change and diarrhea. So we want to distill reliable, robust, and relevant information from global climate models to improve preparedness on diarrhea outbreak. So here's like a schematic. We have the global climate models. We downscale now this rainfall statistics rather than temperature statistics. But since we need to use water model or hydrologic models to simulate water quantity and quality, we need to translate these into daily rainfall using a weather generator. So here this is a case for the Volta catchment in Ghana. And we downscale the wet day frequency and the wet day mean precipitation. And I'll come back to why we do that and not the total rainfall. So for the wet day frequency, it gives an indication of how many days each year we get rain. And we see from the observations that there might be a slight decline, and also the model seem to indicate that there will be fewer rainy days in the future. Here we have much smaller ensembles, just one run per model, because we use a large-scale wet day frequency to downscale the local wet day frequency. So we rely very much on the global climate models to do the right thing. When we look at the wet day mean precipitation or the intensity, we see that the ensemble doesn't really span the observation, so it's a bit poor quality on this, but we still get an indication that the intensity will increase, whereas the frequency will decrease. And these two parameters, the wet day frequency and wet day mean precipitation, will be used as input for the weather generator. So what we do, we have a sample rain gauge data for the past. We use to train both the weather generator to get both the climatological profile correct, but also to get the structure right. And we use the wet day frequency and wet day mean to get the amounts right, and also the number of rainy days that is specified by the wet day frequency. So what we actually make projection of is how often it rains, and also the amount that we get as well. So then we get like an output, which is also a daily series, but based on these inputs here. And if you test it, this is for just test it on the data, on the historical data. We compare the amounts with the simulated amounts in Ghana. It actually does a fairly good job. There's almost a one-to-one correspondence. If you look at the dry spell durations, it's sort of okay-ish. It's not perfect. When I look at the number of wet days, the model does reproduce the level, but of course, the timing is random, but it does a fairly good job. But also the wet day, the wet spell duration is a little bit off, not perfect, but maybe good enough. And if you look at the total rainfall each year, we see that the models does a fairly good job. It does also reproduce the climatology in Ghana with 2 rainy seasons. So the black is observation and the red are the model simulations. The climatology and wet day frequency is well reproduced, so it creates more rainy days at these times a year. And also the intensity is fairly okay, so it's doing a fairly good job. So then we can use this as an input to a hydrological model to study the outcome of say water quality and water quantity like this. But also the statistics in itself is very useful. So if you look at the wet day frequency and wet day mean, we can estimate how many days a year we can expect with more than 20 millimeters. So here is actually an evaluation. This is in Romania. This is also part of the Springs project, and Palermo in Italy, which is also part of the Springs pilot region, study region, and also Akasemo, which is in Ghana. We don't have as long time series in Ghana. But you can see that the black curve here is based on this equation, which is only needs two parameters, as a wet day frequency and the wet day mean precipitation. I will set X here, the threshold, to 20 millimeter. And the red line is actually the observation, or the count from the observation. So we see that indeed these two parameters are very well capture the heavy rainfall events. It's not, I wouldn't go far in the extreme tail, but like for heavy and moderate extremes, it does very well. And for many other sites as well. We can also use these two parameters to estimate the 10-year return value and a 20-year return value. This is when we tested this method for the Nordic region. And we can also use this to estimate a trend in the 10-year return value and 25-year return value, because we have an analytical expression based on these two parameters, so we can derive the trend in them as well. And you see it here, like for the Nordic region, the highest amounts on a daily basis are on the west coast here. And we have, like say, in the north there, it's like it doesn't rain a lot, but we have about 170 millimeters on the west coast here, which is not too far from what we actually observe. And for the 25-year return period, we're sort of stretching it a little bit to where it may become less skillful, but we're looking at 200 millimeters a year. And we can also see that, I'm going to move around here. You can see that the strongest increases in these return values are on the west coast, and this is also where we will experience more extreme changes in daily rainfall as well. So and we see that the 10-year and 25-year return periods is increasing everywhere apart from one site here and here, which was one station which is a bit different to the others. And these maps are based on basically kriging, using elevation as a covariate of all, like a number of sites that we downscaled. So this is what we can do with rainfall. So we downscale the wet day frequency and wet day mean precipitation, and we can actually, and the threshold is 1 millimeter that we use here. And now we can get fairly robust and also reliable results for future rainfall. Another thing is like, another question that is sort of getting more attention these days is artificial intelligence and deep machine learning. And one thing I would say is that it's a different situation for weather, which is present climate, and the downscaling of future climate, for which the training data that we use for is no longer representative because the climate has changed. And there have been lots of studies in the literature where they see that it doesn't, the AI ML doesn't really perform so well when it comes to the future. But there's a solution to that, and that we can use emulation, where you use artificial intelligence trained on regional climate model results, which include both the past and the future, and then you ensure that you don't train them on data which are or auto data type of situation, and you don't rely on extrapolation. But then again, you rely on the RCM giving a good description of what you're looking at and also represent the extremes very well. But then again, the artificial intelligence and machine learning always have this sort of the two ghosts called the black box. We don't know exactly why we get the results, and they're not really reproducible, and hallucinations. So they sometimes come up with some really strange results, and we don't know why. Like they make up things which shouldn't be there. So the question is if they are reliable or robust. And I've written a comment on this on Arxiv because I feel like, there's a pressure to make use of AI and machine learning. But I think, and there's value in the old-fashioned way of doing statistical downscaling, where we put more emphasis on the theory and the mathematics than machine learning is much more focused on the empirical data. Of course, the empirical data is also important for statistical downscaling. But I would say that the mathematical formula and a mathematical theory is always true everywhere and all the time, whereas the data that we sample and use for training is not necessarily so. So statistical downscaling, then you help it with basing it on downscaling these curves of distributions which tend to be more valid. So I will finish off thanking you for your attention, and then I will also just say thank you to Oscar and Julia and Kais and Andreas, who also contributed to this presentation, and also to Kjetil Isaksen, who has taken all these wonderful pictures. And by then I will finish. Thank you.
Thank you. Thank you very much for this very interesting presentation, Rasmus. So you can ask from our presenter. First, I would like to introduce you Vesna Đurđić, who will manage the chat today. She is the president of the Croatian Meteorological Society, and she is very active member of the EMS seminar group. So it's time to ask from Rasmus, and Vesna will check the chat. First, I would like to ask you, Rasmus, if there are advantages or disadvantages downscaling the global climate models, or instead of using regional climate models. So what is your opinion on this? Because in Hungary, we use regional climate models for climate projections, not directly downscaling the GCMs.
Yes, so I think regional climate models is also a way of downscaling in a sense. I would use both actually, and statistical downscaling is computationally very cheap. It requires like understanding of what we're doing, physics, statistics, maybe some training, but I do it on my laptop. So once you have the data, you can do it anywhere with data, because I calibrate with RFI reanalysis, which is global. So I just need local data for the calibration. So they both have different advantages and disadvantages. You really you are restricted to the places where you have good data that you can do your training. And one nice thing with statistical downscaling is that, in our case at least, it involves stages of evaluation. We use something we call common EUFs, where we combine anomalies of the RFI reanalysis on the same grid as a GCM. We have a joint data matrix and then do a EUF on both of them. And then we get an idea of the quality of the regional climate models if they capture the same spatio-temporal covariance as we see in the RFI, that we also can relate to the local variations. So it involves a lot of evaluation as we go along, so we get an idea of how well the global climate models perform. Although this is on aggregated data, because we tend to look at, say, like we tend to use a sample of daily data. So we take a season to say this is a sample. It's not a scale; it's a sample size, and then for daily data. So, but it sort of can be misunderstood as a scale of the data. But the scale is because we downscale the parameters of the PDF. It's more like a sort of sample aspect more than it's like a slower scales. And as I showed you, we can then use these curves to say something about how often we get, say, more than 20 millimeters, or what is the 10-year return value on a daily basis. So you have the scale and you have a sample size, which are subtle but different things. But I would urge everybody to use both regional climate models and also empirical statistical downscaling as well. And because statistical downscaling, you can downscale a huge ensemble, because like with regional climate models, you have to make a small selection, so you are subject to this internal decay variability that Desert al. In 2012 and 2020 showed that one model can produce very different sort of outcome in the future due to chaotic dynamics.
Yeah. Okay, thank you. Interesting. So, Vesna, can you see questions in the chat?
Yes, there is one question. So, Rasmus, could you comment on some of the problems related to data? For instance, data quality, non-stationarity of observational datasets due to urban expansion, land use change, or similar, then insufficient temporal length of most records in many regions to robustly estimate of extremes using statistical methods.
Good question. So we get a very strong indication of the data quality when we do the regression against ERA 5. So if there's a very close match as we see in Northern Europe, we see they are very similar. They have a high correlation. We have an R squared of, say, 9.98. So then we know that the quality is very good. But also we don't downscale single stations anymore. We take a group of stations in the same region affected by the same phenomena, large-scale phenomena, and do a principal component analysis, a PCA, to extract the most common, the coherent signal. And in that way, we enhance the signal to noise ratio. So if there's a problem with a single stations, it will be toned down. Because like if you have random errors, then they will not be correlated. So we use a lot of principal component analysis and UFs, common UFs, and work in this space when we do the analysis. And once we finish, we convert it back to station data. And that way we avoid some of these complications when it comes to data quality. The biggest problem is the gaps of missing data and how to fill in the missing data. And one thing is to try to sweep it under the carpet by looking at past covariance, structure, and fill in based on that. Another way is to use the ERA 5 itself and fill in the gaps with adjusting the ERA 5 by regression. But it's the point is that we don't need to have a perfect description of the data, but enough to be able to carry on with the analysis and do the calibration.
And then another one, could you comment on possible ways to avoid physical inconsistency when purely statistical and machine learning methods produce outputs violating physics, like negative precipitation, unrealistic spatial coherence, etc.?
Again, because we are not any more downscaling weather point by point. We're downscaling the parameters describing these distribution curves. So then you don't get that problem at all. Because we downscale the statistical properties rather than individual aspect. But once the way we design the downscaling statistically, so we look at the physics. And what we do is actually we use large scale temperature to downscale local temperature. So we have an equation and the physical units on the both sides should be the same to make sure that we don't have to run into non-stationarity problems, but also as close as possible to each other. So that there's no sort of expectation of that they would be different. It would be a different story if I used a predictor of many different variables, like as it tend to do for like each data point. You need many different variables of different heights, and then you run into that problem. But also, like say for rainfall, we use large scale wet day frequency to downscale the local wet day frequency, or maybe use sea level pressure anomalies, which is also very good. When it comes to wet day mean precipitation, we use large scale wet day mean precipitation to downscale the local wet day mean precipitation. Sometimes it does, like the data is not good enough for that. We tried with temperature, like there's a thermodynamic aspect to it. Sometimes that doesn't work, but we know that the total rainfall is the product between the wet day frequency and the wet day mean precipitation times the number of days. So we can estimate the wet day mean precipitation by dividing the total rainfall divided by wet day frequency. It's not exactly the same because we have a threshold of 1 millimeter, but we avoid this unphysical picture. And this is also part of the design of the strategy, and which makes it reliable and robust.
And then some specific one. For instance, if I want to retrieve information on daily temperature, maximum and minimum, in a region of Italy for 2040, is it better I make an ensemble of all the projections available in the period 2035 to 2045, or I can take the data exactly of 2040?
That's a good question. If you have a large ensemble of 300 runs, it doesn't really make a big difference. But if you have a small ensembles, then because of random sort of internal variability, some models will be cold and some will be warm. So, but you can sort of fit like a polynomial to the upper and lower limit to do that. One thing is also like you can use the Gaussian distribution and the Bayesian statistics, where you look at, say, the 95th percentile of that ensemble member, and then you can say, okay, that would be the mean for that year, and then you can take the Gaussian distribution. And it's because you don't have to get far into the tail to get like a high value, but you wouldn't really look at the maximum and minimum, but more like sort of the upper quantiles rather, or like probabilities.
And another one, which criteria are applied in the selection of global climate models to feed the downscaling scheme?
Yeah,
I use downscaling scheme applied at seasonal level.
Yes, so I use all that I can. It takes me 1 minute or two to downscale one model. So I use all of them, and then I'll see if any sort of distinguishes as being different. They all do fairly well actually when they use common UF as a basis for the analysis. And yes, I tend to either I would do global for rainfall, but I would use like winter, spring, summer, and autumn to and distinguish between the 4 different seasons. Because the trends may be seasonally dependent, or we know they are.
No questions so far, but I have to say that everybody, congratulations to your talk, and say that it was a great talk.
Thank you very much. And if you have any questions, don't hesitate sending me an email. There are some. I can also share the presentation if you like as well, so you can have. There's some references there.
Another one just came out. Hi, you mentioned that machine learning methods are problematic for downscaling of climate projections. I have a machine learning based downscaling model that currently validates well on historical data. What are the potential issues of applying it to climate projection data? And what are the methods I can use to validate the results of a machine learning climate projection downscaling?
Good question, and I expect they will validate very well on historical data. I was just examiner for Nilesh Rapal in Australia, and so he and also others have actually tried to evaluate how they do perform in the future by testing them on regional climate model simulations, where they both have historical data and future data. And what he found is that if you only train them on historical data, they don't capture everything in the future. So, so I would suggest using them in emulation mode of a weather forecasting or seasonal forecasting. But you have to find ways of actually testing whether they are able to predict the future changes in say extremes. And we have there have been attempts to use machine learning or deep neural nets in downscaling climate change since the end of the 1990s. So there's been quite a long experience. Now there is, of course, more data and maybe more advanced methods, but I think it really needs to be evaluated and also benchmarked against proper, like the best statistical downscaling methods, because you can always find some methods which are maybe not performing so well and beat that. So, and that is one of my criticism of some of the work done so far, is that they have been taken fairly lightly on what is available on when it comes to statistical downscaling or regional downscaling. And I think there's a lot more work to do and to do the benchmarking.
Thank you.
So I cannot see more questions. Vesna, can you see more?
No.
Or just raise your hands if you would like to ask, if possible. I'm not sure. Is it possible to raise the hands for participants? I'm not sure, but okay. So thanks again, Rasmus. It was very interesting presentation, and you answered all the questions properly, I think.